Welcome back to another episode of Introductory Organic Chemistry. Today we're going to talk about the hydrogenation of alkenes and alkynes. And since we don't have any follow-up from last lecture, we're going to get right into it. So hydrogenation reactions are very easy to do. Typically you can take an alkyne or an alkene, and with the right catalysts in the presence of hydrogen, you'll be able to just add hydrogen across the double or triple bond. Normally when we have double or triple bonded compounds, we can refer to them as unsaturated, and it's possible to saturate them with hydrogen, which is why you have unsaturated fats and saturated fats, for instance. Now, if you're going to do a typical hydrogenation, you won't react with too many other functional groups, but certain metals like palladium will tend to react with anything if left for long enough. Palladium is promiscuous. I always joke with the people that I'm tutoring that palladium is like the hoe of chemistry, where like if you leave it long enough, stuff will happen. So if you wanted to do something where you don't have a heterogeneous catalyst, because most of these catalysts like platinum, palladium, or nickel-derived catalysts, they're going to be in the solid phase, and so you can filter them out. Although there are soluble ones that you can get, but they tend to be very specific and kind of just an excuse for organic chemists to get papers, or organometallic chemists to get papers rather. Not actually contributing too much to the field, but you'll see like a million examples of different catalysts, so we're not going to talk about them too much here. Okay, so if you use palladium metal, which is like most commonly used, it's absorbed over a surface, something like calcium carbonate or carbon, and it could be 10% palladium or 5% palladium when you weigh it out. So usually 10% palladium on carbon is the most common thing you see. Now, if you're working with palladium on carbon, it's highly flammable because carbon is flammable, plus the palladium on there can help catalyze the combustion of carbon. And so if you like accidentally aerosolize some of the powder, it can just spontaneously ignite an air without any spark because the catalyst is already present and it helps activate oxygen to react even faster. If you are using this strategy, so whether it's nickel, palladium, or platinum, most of the time, you're just going to hydrogenate everything. Now, like benzene rings, other very stable systems, heteroaromatics, they don't tend to be reduced under normal conditions, and you'd have to use massive, massive high pressures and sometimes also elevated temperatures to fully hydrogenate those. So most of the time, if you're just doing like room temperature with palladium on carbon in a protic solvent with a balloon of hydrogen, that'll usually do the job, and that will usually convert most of the starting material. But sometimes if you have a really stubborn double or triple bond, it's necessary to use pressure. But even though you see people using pressure quite often, it's usually not necessary. You can just get a balloon of hydrogen, and then when the reaction's done, the balloon will stop, having hydrogen go into the vessel, and eventually the balloon will just stay the same size. So if you do this in like a round bottom flask with a rubber stopper or a rubber septum with just like a needle bleeding in hydrogen into the reaction, that's usually sufficient. Now, the downside is if you have other functional groups such as a benzyl ether or a nitro group or benzyl esters, carbamates, imines, other things that could potentially get reduced, they could cleave those as well. So in the case of a benzyl ether, this will actually reduce the benzyl ether to toluene, and then the ether just gets converted to an alcohol. And so it's kind of a weird reaction, but benzyl ethers are fairly labile to hydrogen and palladium on carbon. So yeah, palladium is very promiscuous. If you're going to use it, just be aware that other reactions can occur. But most of the time, if you have a simple reduction to do, you're going to use the most straightforward conditions. You're not going to use obscure methods. You don't need to pick the special conditions if you have a very easy substrate to work with. As I was saying, heat and pressure can help, but they're usually not necessary. Okay, so the general mechanism of this reaction, this is kind of oversimplified, but in a heterogeneous catalyst, you have like the surface of the metal. So in this case, it's palladium. If you have hydrogen in close proximity, it can react with the palladium, and you have in close proximity two protons which are now connected to the palladium. You can think of them as hydrides as well as like H+, because palladium easily does oxidative addition to basically anything. Like acetic acid will react with palladium 0, and you'll get palladium 2 acetate hydride. And so palladium is super promiscuous. Okay, and so in this case, because both of these hydrogens are side by side on the surface of the palladium, you're always going to get syn addition of these two hydrogens to the alkene or alkyne. So in the case of a cis double bond like this, you're going to have hydrogens added like this. And in the case of a trans double bond, you're still going to have them added in the same rotation, but the R group would be pointed down instead of up. So depending on what kind of saturated compound you might want to make, you might have to choose a different alkene to make, whether it's cis or trans would give you what you're looking for. Obviously in ring systems this wouldn't be useful because you can usually only have cis double bonds unless you have very, very big rings. Okay, So some examples of the use of just general normal shotgun hydrogenation. Here you can see there's an alpha beta unsaturated carbonyl. This reacts with platinum oxide and hydrogen, and they didn't give reaction time for this reaction, unfortunately. But because this is electron deficient, it'll be a little bit slower, but these will still typically go. Now you might wonder why they use platinum oxide instead of palladium on carbon. Oftentimes, several catalysts will be screened, and then just whatever works is what's used. So in this next example, you can see palladium on carbon is used in combination with this odd diphenyl disulfide catalyst, which in the case of this transformation, they found that it accelerated things. And so this just helps either activate the palladium or activate the hydrogen using like thiols instead of disulfides, just as a catalyst. Okay, so you can see some decent functional group tolerance, typically high conversion, relatively fast. Now, if you wanted to hydrogenate an alkyne, but you didn't want to go all the way to the alkane, it's possible to use either a poison catalyst, like Lindlar's catalyst, or you can use a nickel boride species called P2. So P2, there's P1, it just involves some nickel boron complex. It's complicated how these are made. Usually they just take like sodium borohydride as well as some nickel salt, and then they work it out and you get some sort of nickel species. Now, in the case of the Lindlar's catalyst, what happens is there's quinoline, and this just prevents any further addition to the alkene. In the case of P2, like the mechanism's more complicated, and because these involve transition metals, I'm not going to go into too great of detail about mechanism because it's not super well understood. But they did figure out if you poison a palladium catalyst, you can get just reduction to the cis-alkene without over-reduction. So this will always give you the cis-alkene the cis-alkene. But the reason for this is, again, hydrogens being added to the same side. So if you want to get a trans-alkene, you have to do different conditions, which we'll talk about in a minute. So some examples of the Syn reduction of alkynes to cis-alkenes. Here you can see this alkyne was reduced with Lindlar's catalyst in 24 hours in high yield. And in this case, we have another alkyne, which is converted using P2 into high conversion as well in only 2 hours. So if you wanted to get a trans-alkene, you have to do a dissolving metal reduction. So this is most commonly done with sodium metal in liquid ammonia. And I'm going to put a card to a Nile Red video where he shows the formation of solvated electrons. So solvated electrons, when you put an alkali metal in a solvent like liquid ammonia, you'll get this deep blue or deep bronze colored solution because the sodium is able to give its electrons and there's free electrons flowing around in the solution. And so the sodium cation is separate, and the electron is just able to freely flow throughout the whole solution. And so you can do some neat chemistry using solvated electrons. One reaction that's commonly done is a Birch reduction. So if you did this to a compound with a benzene ring, you might have to worry about a Birch reduction occurring, but we haven't talked about the Birch reduction yet. Okay, so you get a nice dark blue solution. And the way that this mechanism works is first you get the alkyne. There's a single electron transfer with this half arrow, which is what I've shown here. Is this half arrow's radical arrow. This then splits to a radical anion. The anion is then able to abstract a proton from the solvent, the ammonia, and this forms sodium amide as a byproduct. Then in the second step, this radical is further reduced to an anion, a carbanion, which can then abstract a proton from the ammonia, giving us the trans-alkene, which is more thermodynamically stable than the cis would be. And so some examples of this include the reduction of this alkyne here. In this case, they didn't have any issues with Birch reductions occurring. Usually a Birch reduction would also have an alcohol present, and so you could see that they did this in toluene at a little bit lower of a temperature than a Birch reduction, and they get this product in high yield. Now another example here has the reduction of this alkyne to this alkene, and they get quantitative conversion. They didn't give time, however, in this case. Okay, so there are still some other approaches for reducing double and triple bonds. One of them is the use of diimide. And so diimide is a really, really convenient reagent because unless it reacts with itself, you'll just get nitrogen as a byproduct, which is pretty good. Good atom economy. Now the disadvantage is diimide can reduce itself because it has an N double bond N, and if it reduces that, you'll just get hydrazine and nitrogen gas. Now, one of the ways that diimide is prepared is just through the oxidation of hydrazine. So something like oxygen or a lead oxidant or basically any oxidant with enough oxidizing power can oxidize hydrazine to diimide, and then it can just be used in situ. However, hydrazine can react with a lot of functional groups, so you kind of have to be careful about using that approach. There are other functional groups that can typically be hydrogenated using like palladium on carbon and stuff, but there's much greater functional group tolerance in the case of using diimide. So you could have like a peroxide, for instance, and it wouldn't reduce the peroxide to a diol. So you can have a lot of sensitive functional groups that would not get touched by the diimide. It is worth noting, though, that electron-rich alkenes react faster. So if you had multiple different alkenes, one of them was a Michael acceptor, and one of them was just a typical alkene with R groups, that the one with R groups is going to react faster. So another convenient way to prepare it, aside from the oxidation of hydrazine, is to use potassium azo dicarboxylate, which is just, instead of the two H's on the diimide, they're just carboxylate groups. And then in a protic solvent, or like a protic solvent with a weak acid like acetic acid, you can just generate it in situ. And this salt can be prepared fairly easily. And so it's another solution that gets around the hydrazine problem. Obviously, some hydrazine can still form in situ, though, so it's something worth keeping in mind. Okay, so the mechanism of this reaction is relatively straightforward. Alkene attacks a proton, the NH becomes the N2, then the other proton with its electron density acts as a hydride and attacks the other carbon, and you still get syn addition to the alkene or alkyne. Now, one example from the literature is the use of the potassium azo diimide salt, and they use deuterated acetic acid, just the OH is an OD instead of just like having the whole thing deuterated. You can get away with just deuterating the acidic proton. And so in this case, they show that they get addition to the top face of the alkene, and they do that with deuterium labeling. So deuterium is just hydrogen 2. It's got one neutron and one proton, and it's a useful way to tune out mechanisms of reactions, for instance. In this case, because there's already two protons on this alkene that are just hydrogen 1, those are facing down, and they're able to tell that based on coupling constants to this adjacent position. Okay, so if you have a Michael acceptor, and this is just an alpha-beta unsaturated ketone or something like that, and you wanted to just reduce that alkene in the presence of other alkenes, you can use something called Stryker's reagent. You can do a Stryker reduction. And so Stryker's reagent is a hexamer, which just means that there's 6 triphenylphosphine copper hydride units per 1 active mole of the reagent. Now, the disadvantage is it's not stable in air. If you use a different complex of copper 1 hydride, sometimes you'll get other reductions. So Stryker's reagent on its own is like probably the most robust for this transformation. So you have to like handle this very carefully and store it in a glove box. And if you don't, it'll usually decompose, in my experience, anecdotally. Okay, so you can use enough Stryker reagent that you don't need an external reductant, because it's a hexamer. You can use like a sub-stoichiometric amount, but it could still be a sufficient amount of hydride to reduce your alkene. Now, if you wanted to use it as a catalyst, you can do that too. And so you could use hydrogen or a hydrosilane reductant. However, with certain silanes, you might worry about getting, instead of getting ketones or aldehydes out, you'll get enol ethers, which actually could be useful. So you could add in a silochloride to these reactions, and it'll actually trap the copper enolate that forms as a TMS enol ether. So under some conditions, aldehydes and ketones are reduced, but this tends to be fairly substrate specific. In general, though, it can be a pretty good method of selectively reducing Michael acceptors. If you wanted to avoid this but achieve the same sort of thing without using copper hydride, you can also use Hansch esters, which typically work as good hydride donors in the presence of acids. However, most of these transformations are done for enantioselective variants rather than just general, I have an alkene I want to reduce. Okay, so one example from the literature is the reduction of this Michael acceptor. Here you can see hydrides added here, and this other alkene isn't touched. It only takes 1 hour, and they use this substoichiometrically, but again, because there's 6 units, there's several molar equivalents still, 2 or 3, I believe. So they do this without any external hydrogen source. The copper hydride is the source of hydrogen here. Now, the nice thing about this is alpha-beta unsaturated carbonyls can be prepared via aldol condensations, but they can also be prepared using the Wittig reaction or the Horner-Wadsworth-Emmons reaction, which is a topic we'll talk about in future videos. I just wanted to highlight that these are very easy motifs to make. It's a lot easier than building this whole thing on here, like at the sp3 stage. Now, you could methylate this, obviously, but if you had if you're trying to just make an enolate and an alkylate here or here, you might run into some challenges. So there's cases where using a Wittig or a Horner-Wadsworth-Emmons can be really advantageous. Okay, so for this lecture, I'd like to assign 3 practice problems. First, propose conditions for converting this diene here into the alkene on the left and the alkene on the right. In the next problem, I want you to show how you can convert this alkyne into a cis-alkene. And finally, I'd like you to show what the product of the reaction shown here would be. This diene is treated with palladium on carbon and hydrogen. What sort of reduction product forms? And so with that, I hope that this has been a really useful video on hydrogenations of alkenes and alkynes. And if you have any comments, please leave them below. Have a great day.